In this video, we are going to look at chemical bonding. We are going to compile all the videos for this chemical bonding series and put it into this single video. So get ready for the long journey. Whenever someone talks about stability of atoms, they will never forget talking about noble gases. This is because we know that these gases basically are kind of inert. They never want to participate in reactions unless when forced to. So most atoms also want to be kind of stable. When something is not, it's kind of stable because it's not trying to react with other elements. It wants to maintain form. So these noble gases kind of are like the role models of these other atoms that want to gain stability. So noble gases are well known for having a fully filled outermost energy level. That means the last energy level has the maximum number of electrons. So all noble gases will have 8 electrons, with exception of helium, which has only 2 electrons, just because the first energy level can have a maximum of 2 electrons. So whenever we have atoms combining to form molecules, there is a force that will always be developed that can keep these atoms together. And this force that links the atoms in a compound is called a chemical bond. However, it's not always necessarily that we shall have atoms. We can also have ions together to form a chemical bond, as we shall see later on. The sole purpose of any atom, whenever it's trying to form a bond with another atom, is to try and obtain a stable electronic configuration, and with that we mean one that is always similar to the noble gas electronic configuration. When you look at the table below, we have helium. Helium has 2 electrons, and when you look at helium, it has 1 energy level. This is our first energy level, second, third, fourth, and so on. So helium has only 1 energy level, and it's the outermost, and in this case it has 2 electrons, and this is the maximum number of electrons that can be obtained in the first energy level. That's why helium is able to be stable. When we go to neon, neon has 10 electrons. However, it has 8 electrons in the last energy level. Argon also has 8, krypton, and the rest. So one thing you realize is that apart from helium, all the other noble gases have 8 electrons, which is the maximum number of electrons these energy levels can have. And this has been associated with these elements being stable. And as such, all other atoms, whenever they are trying to bond, they want to ensure that they have at least 8 or 2 electrons in their last energy level so that they become stable. So we can summarize what we have first seen in a few lines. We have noted that atoms always combine to ensure that they achieve the inert gas electronic configuration so that they become more stable. And we had seen that it requires these atoms to have the maximum number of electrons in their outermost energy level. You can read about the octet rule. This talks about the need for an atom to have 8 electrons to be stable. However, for some atoms which have only 1 energy level, they just basically need 2 electrons to become stable. So what can an atom do to achieve an inert gas electronic configuration? There are actually 3 possible ways for that to happen. The first one is it can electrons so that it becomes stable, and in this case it will lose those electrons to another atom. Let's take a scenario of sodium. Sodium has atomic number 11. That means the electronic configuration of sodium is 281. So sodium can lose the outermost electron, this one, to another atom, say chlorine. So it will lose one electron, and the new electronic configuration will be 2,8. And in this case, this will obey the octet rule that we had just seen. The second example could be for aluminium. Aluminium has atomic number 13, and that means electronic configuration is 283. So aluminium will need to lose 3 electrons so that the new electronic configuration becomes 2,8, maximum number of electrons in the last energy level. So in this case, sodium has lost this 1 electron, while aluminium will lose these 3 electrons. So this is an example to show that some atoms can lose 1 or 3, and an element which can lose 2 can be magnesium. Try it out and see how stable it will be. The second method is by gaining 1 or more electrons from another atom. The first one was losing 1 or more electrons, and the second one is gaining. So atoms with 6, 5, and 7 electrons in their outermost shell can always gain 2, 3, or 1 electron to attain stability. Let's take an example of chlorine. Atomic number of chlorine is 17, and that means electronic configuration of chlorine is 287. So for chlorine to become stable, it will actually have to gain 1 electron so that the new electronic configuration becomes 288. So it can't lose 7, it will gain 1 electron. And this is an example of an atom gaining 1 electron. And because it now has 8 electrons in the outermost energy level, this is identical or similar to the electronic configurations of noble gases. So atoms that have 5, 6, 7 electrons in the outermost energy level, like chlorine has 7, can gain 3, 2, or 1 respectively to attain stability. The third way is by sharing 1 or more electrons with another atom. So still, atoms with 4 to 7 electrons in the last energy level can do so by sharing electrons. Let's take an example of chlorine. We are sketching the outermost energy level of chlorine. Remember, electronic configuration of chlorine is 287. So we shall need 7 electrons. So we have 1, 2, 3, 4, 5, 6, 7. However, this chlorine will need to bond with another atom so that they can share 1 electron. So we shall sketch another atom of chlorine. It also has 7 electrons in the outermost energy level. 1, 2, 3, 4, 5, 6, 7. So you realize that the chlorine atom in red and in blue, they all share certain electrons. The 2 electrons in the center are the ones being shared by both electrons. This electron 1 and electron 2. So if we are to count the number of electrons of the red chlorine atom, we shall have 1, 2, 3, 4, 5, 6, 7, 8. And in the same way, the one in blue will also be having 8. So because the electrons being shared are for both atoms, so the atoms no longer have 7, but they have 8 electrons in the outermost energy level. So sharing of electrons is another way of obtaining stability. So one thing to note is that whenever a nonmetal becomes a charged particle, the name slightly changes. For example, we had a chlorine atom and it changed to a chloride ion. When you have an oxygen atom, it will change to an oxide ion. So we have that slight name ending that changes. However, we also have some common radicals that can exist as negative ions. So we have the nitrate, the carbonate, and the phosphate. For the positive radicals, we have the ammonium radical. So these two sentences, we had them on our previous slides. However, what do they mean? When we say the number of positive charges carried on a cation is equal to the number of electrons lost by the metal, let us assume our cation is this one here, magnesium 2+. This 2 here, the number of the positive charge, is always equal to the number of electrons that have been lost. This is the electronic configuration of a magnesium atom. However, it loses these 2 electrons so that it becomes 2, 8. So that's why we say the number of positive charges carried on a cation, in this case it is 2, is equal to the number of electrons lost by the metal, and still in this case there are 2 electrons. The same thing happens for the non-metals. The number of negative charges an anion carries is equal to the number of electrons gained by the non-metal. We had a look at the chloride ion with a minus charge. It had 2, 8, 7. However, it gained 1 extra electron and it obtained a new electronic configuration of 2, 8, 8. So you realize that here we have the number is 1, although we don't write it. We can't write it like I had shown you initially. You can't write it as 1 minus because it's the same thing. So this is 1, and here we have 1 electron that has been gained. So the number of negative charges is always equal to the number of electrons that have been gained. Thanks for being patient up to this point. We come towards the end of our video and we have our top 2 questions. Question 1. Why do metal ions carry positive charges? Question 2. The number of negative charges an anion carries is equal to the number of electrons gained by the non-metal atom. True or false? Feel free to let me know in the comment section what you think about these 2 questions. By now, we know that an atom is made up of 3 subatomic particles: electrons, protons, and neutrons. Electrons are negatively charged, protons are positively charged, while neutrons have no charge. And we know that an atom contains an equal number of protons and electrons. So positively charged protons are always equal to the negatively charged electrons. And as such, this atom is electrically neutral because it has no charges and it cannot conduct electricity. So an atom has no charge. So when you look at this image, it can help us analyze this concept better. When you look at this atom here in the nucleus, it has 7 protons. These are positively charged. However, it also has 7 electrons. These are negatively charged. So if you have 7 positive charges and 7 negative charges, the overall charge, if at all these charges cancel out the effect of the opposite charges, we shall have 0. So basically an atom has no charge. We have seen that an atom is a neutral particle. So in the same line, we can say that an ion is a charged particle, one that does not have zero charge, so a charged particle. So how is it formed? It's basically formed when an atom, which is a neutral particle, loses or gains one or more electrons. However, we know that atoms can either be metals or non-metals, and in this case we are going to start with the metallic nature. So a metal loses its outermost electrons to form a positively charged ion, and in this case we can call it a cation. And we shall later realize that the number of positive charges carried in a cation is equal to the number of electrons which will be lost by the metal atom. So how do metals become charged particles? In this case we have sodium. Electronic configuration of sodium is 281, meaning that sodium has 11 electrons. And for this sodium atom to have 11 electrons, it must also be having 11 protons. However, sodium will lose one electron under the column of electrons lost. You realize the electron it will lose is this outermost electron, and then it will have two energy levels, which is 2, 8. So under our ion side, we shall realize that sodium has 10 electrons because it has lost 1. However, it will still be having 11 protons. So before the sodium atom losing its electron, it has 0 charge because it is still an atom. But on losing this single electron, it now has an overall net of 1 positive charge, because 11 protons with 10 electrons, it means you have a net charge of 1 positive charge. That's why on the sodium ion we write the symbol and then a superscript representing the positive charge. If at all there are 2 positive charges, we write a superscript with a 2 plus, like you can see here on calcium. Feel free and pause and try to do the same workout with calcium and aluminium and see how these corresponding charges come about. So if at all the previous presentation was quite challenging, hopefully with this diagrammatic representation of atoms we shall be able to clear out some of those doubts. So when you look at this sodium atom here, you realize that this sodium atom has 11 protons as shown inside the nucleus. So here we have 11 protons, and then it has 11 electrons. If we are to count these electrons, we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Basically we have 2 in the first energy level. This is our first energy level. Then we have 8 in the second energy level, and then we have 1 electron in the outermost energy level. However, during the formation of the ion, we shall realize that this 1 electron is lost, and when this 1 electron is lost, that means this outermost energy level will have to disappear because we don't have any present electron here. That's why on our right hand side we shall realize that we actually have 2 energy levels, 1 and then 2, and the new electronic configuration will be 2, 8, because it will have lost this 1 electron. However, the number of protons will remain 11, so we still have our 11 protons, but electrons have reduced to 10, and that means you'll have an extra positive charge of 1. That's why we shall have to represent our sodium ion in this format to show to people that we have an extra positive charge. So we write on the right hand side of the symbol a superscript of a plus sign. Because it's 1, we don't need to write it in this format, because just writing it as sodium Na plus can do the same job. We can't forget talking about a hydrogen atom. A hydrogen atom contains 1 electron and 1 proton in the nucleus. Usually it can lose an electron to form an ion with a positive charge. When this 1 electron is lost, it will only be left with a small positively charged nucleus, and so we can write the symbol of the ion as H plus, because it has 1 proton and 0 electrons. Now let's get to the nonmetals. If metals become ions by loss of electrons, nonmetals will readily gain 1 or more electrons to become stable, and in that form they will be forming a negatively charged ion, which we can call anion. And still we shall later discuss and realize that always the number of negative charges on the anion will always be equal to the number of electrons that have been gained by that given nonmetal, as we shall see later on. So how do nonmetals become ions? Let's take an example of chlorine. Electronic configuration of chlorine is 287, meaning that the total number of electrons it has is 17 electrons. And because we are looking at the atom side, that means we should have also 17 protons, so that the atom is neutral. However, whenever an ion is being formed, nonmetals will have to gain some electrons, and in this case, to gain a stable electronic structure, it will have to gain 1 electron, and in this case it will form 288, an increase in the number of electrons. That means now this chlorine ion will be having 18 electrons, but the number of protons in the nucleus are still 17, and that means we have more negative charges than positive charges. So the overall charge of this particle will be 1, which is negatively charged. So in this case we shall write the symbol of the atom, and then we shall write a superscript on the right hand side of minus, because it's only 1 charge. However, for some ions like the oxygen or the oxide ion, we shall have a 2 minus to show that we have 2 negative charges, or 2 electrons were gained. So feel free and pause the video and try out the same working for oxygen and nitrogen and see how we obtain the corresponding symbols for these ions. So using chlorine as our reference nonmetallic atom, we shall see that it has 7 electrons in the outermost energy level. However, for it to be stable, it must have a fully filled outermost energy level, and as such it will have to obtain 1 electron so that it gains and obtains a 288 electronic configuration. In this case, at the start it had 17 electrons with 17 protons in our nucleus, but on gaining that 1 electron, it will now be having 18 electrons. However, in the nucleus it still has 17 protons, and we shall have an overall charge of 1 minus charge. So we shall have 1 but a negatively charged charge. That's why we shall have a chloride minus as the symbol for the chloride ion. So one thing to note is that whenever a nonmetal becomes a charged particle, the name slightly changes. For example, we had a chlorine atom and it changed to a chloride ion. When you have an oxygen atom, it will change to an oxide ion. So we have that slight name ending that changes. However, we also have some common radicals that can exist as negative ions. So we have the nitrate, the carbonate, and the phosphate. For the positive radicals, we have the ammonium radical. So these two sentences, we had them on our previous slides. However, what do they mean? When we say the number of positive charges carried on a cation is equal to the number of electrons lost by the metal, let us assume our cation is this one here, magnesium 2+. This 2 here, the number of the positive charge, is always equal to the number of electrons that have been lost. This is the electronic configuration of a magnesium atom. However, it loses these 2 electrons so that it becomes 2, 8. So that's why we say the number of positive charges carried on a cation, in this case it is 2, is equal to the number of electrons lost by the metal, and still in this case there are 2 electrons. The same thing happens for the non-metals. The number of negative charges an anion carries is equal to the number of electrons gained by the non-metal. We had a look at the chloride ion with a minus charge. It had 2, 8, 7. However, it gained 1 extra electron and it obtained a new electronic configuration of 2, 8, 8. So you realize that here we have the number is 1, although we don't write it. We can't write it like I had shown you initially. You can't write it as 1 minus because it's the same thing. So this is 1, and here we have 1 electron that has been gained. So the number of negative charges is always equal to the number of electrons that have been gained. Thanks for being patient up to this point. We come towards the end of our video and we have our top 2 questions. Question 1. Why do metal ions carry positive charges? Question 2. The number of negative charges an anion carries is equal to the number of electrons gained by the non-metal atom. True or false? Feel free to let me know in the comment section what you think about these 2 questions. So this type of bonding is called ionic bonding because it involves the presence of ions. Remember, ions are charged particles, and in the same way the compounds which are made up of ions will also be known as ionic compounds. In our previous video, formation of ions from atoms, we had a look at cations and we said these are positively charged particles while anions are negatively charged particles. Whenever you have 2 opposite charges, there will always be a force created between the 2, and this force will be an attraction force. So the cations and anions are always held together by the strong forces of attraction, and these will be called ionic bonds or electrovalent bonds. So the process of these atoms sticking together is what will be the bond. So ionic bonds will be formed due to the Coulomb's force of attraction between opposite charges. Just like atoms have an equal number of protons and electrons, even an ionic bond has an equal number of positive charges and negative charges, and we shall see what we mean by that. And because of that, we shall always have an overall charge being 0 for an ionic compound. So what do we mean by equal number of positive charges and negative charges? Let's take an example of this common salt, sodium chloride. Sodium chloride contains sodium ions, which are positively charged, and the chloride ion, which is negatively charged. You will realize that we have one positive charge and we have one negative charge. However, when these two are together in our compound form, sodium chloride has no charge, so we can write it as NaCl. So the overall charge of this compound is 0, even if the individual ions have different charges. So a compound which is ionic will always have an overall charge of 0. Another example you can look at is calcium chloride. When we look at calcium chloride, we shall have calcium chloride. You will realize that we shall have one calcium ion with two chloride ions. But still you will see that the total charge, here we have a 2 plus, and this side we have 2 negative charges. So still the overall charge of the calcium compound, this one here, will be 0, because the 2 positive with the 2 negative will cancel out to have an overall charge of this compound to be 0. In this table, we are going to look at the formulae and nomenclature of some ionic compounds. So here we have the naming, the formula, and the ions present, because we are looking at ionic compounds. We have aluminium oxide. It contains aluminium and oxygen is 0. And we have aluminium ion, which is aluminium 3 plus, and the oxide ion, which is O2 minus. Another example we have is ammonium chloride. It contains a cation, which is ammonium, and an ion, which is the chloride ion. We have calcium hydroxide containing calcium ions and hydroxide ions. So here we have our first radical. Some other compounds, we have calcium nitrate containing calcium ions and nitrate ions. We have magnesium chloride containing magnesium and chlorine, but in solution form, or the ions present, we shall have magnesium ions and chloride ions. And then lastly, we can have a look at sodium. Sodium is a metal. Then we have our carbonate, which is a radical. We shall have sodium carbonate as the formula of the ionic compound, but the cation present will be the sodium ion and the carbonate ion. So you can feel free to pause the video and check out other compounds. But one thing to note, we have positive charges and negative charges coming together, because there must be ions present. That's why we call them ionic compounds. One thing you might have noticed on our previous table is that we were mainly dealing with metals and non-metals. However, we have some ionic compounds that are made up of non-metals only. But in most cases, ionic compounds will always be made up of a metal and a non-metal, with the exception of ammonium chloride. Feel free to go back and see ammonium chloride. It has no metal in it. So we have ammonium chloride. Remember, it contained the 2 ions, ammonium and our chloride ion. So nitrogen, hydrogen, and chlorine, they are all non-metals. We have no metal present. So ammonium chloride is the only ionic compound in our previous table that does not contain a metal. So whenever we shall be dealing with a bond that involves a metal and a non-metal, we shall always call it ionic bonding, as we shall see later on when we are looking at the formation of an ionic bond. Why do we come to a conclusion that a metal and a nonmetal will always be an ionic bond. So in our next video, we shall have a look at formation of an ionic bond. With this brief introduction on ionic bonding, let's have a look at our top 3 questions. Question 1, name the ions present in calcium nitrate. Question 2, ionic compounds are made up of a dash and a dash. You try and fill in appropriately. You can let me know in the comment section. Then question 3, give an example of an ionic compound made up of only nonmetals. That should be easy to answer. Atoms that are always to form this type of bond will always have a change in their electronic configuration because they have to become charged particles. They have to become ions. In this case, for example, if we have a metallic atom, these ones are well known for losing electrons, and the due process they will form cations, which are positively charged because they will have more protons than electrons. However, when you look at nonmetals, for them they will always ionize and form the corresponding anions by a gain of electrons. In the due process, they will have an overall charge of minus because they will have more electrons than protons. So when you have a cation which is positively charged, and then you have a negatively charged ion, we shall always have a force between these two, and this force is the electrostatic force of attraction that we are talking about here. And it's this force that will always keep these different ions together, and it's what we shall call the ionic bond. Let us look at our first example, which is sodium chloride. We need to know how it is formed. Sodium chloride is also known as common salt or table salt, the one you normally add to your food to improve its taste. So whenever you have a sodium atom placed in chlorine, it can react, if at all it's hot, resulting into the formation of sodium chloride. So basically sodium reacting with chlorine to form sodium chloride, something like this. So let's balance with the half. Obviously chlorine will be a gas. So in this case we want to see how this sodium chloride is formed. So when you look at the two atoms, we have the sodium atom and the chlorine atom coming from the chlorine gas. So our sodium atom here has electronic configuration of 2, 8, 1. As you can see, this one electron is shown here in red. So this one electron, because sodium is a metal, will be lost so that our sodium atom can now become 2, 8. However, it will not be lost to no other atom. It will be lost to the nearby chlorine atom because we have placed this hot sodium atom in chlorine gas. So this sodium atom prefers losing this one electron so that it becomes stable. However, when you look at our chlorine atom, it has electronic configuration of 2, 8, 7, and it wants to obtain one electron so that it becomes 2, 8, 8, electronic configuration of noble gases. So in the due process, this one electron from sodium will be taken by the chlorine atom so that the chlorine atom gains one more electron to become stable. So when you look at what will be formed, we shall see that here we shall have new ions being formed. The sodium atom no longer has 3 energy levels. It now has 2 energy levels. This is energy level 1 and this is energy level 2. When you come back to our first image, it had 3. 1, 2, 3. But now because it has lost this outermost energy level, it now has only 2 energy levels. 1, 2. That's why here we are having a sodium ion. However, it has a positive charge as well. So at this point we have a sodium ion, Na+, while our chlorine also gained an extra electron. As you can see, it's red. It's the one that came from this sodium atom. So our chlorine atom will now become a chloride ion with Cl- because it will be having more electrons than protons, as we had seen in one of our previous videos, how we form ions from atoms. So whenever we have this cation, which is positively charged, and this anion, which is negatively charged, opposite charges attract. So this attraction is what keeps these atoms together, as we are going to see in our next slide using a different example similar to chlorine. So that's all about sodium chloride. Basically, the sodium atom loses its one electron. However, this one electron is taken by the chlorine atom, so that they become 8 electrons in the outermost energy level of chlorine. But in the due process, the charges come into play, because when sodium loses one electron, it becomes positively charged, and then chlorine becomes negatively charged. Then these opposite charges attract and keep these ions together. Let us now look at the summary of ionic bonding using sodium fluoride. That means sodium is reacting with fluorine. When you look at this clip here, it shows that we have a sodium atom which initially has its outermost electron, and this outermost electron is then lost to fluorine. Fluorine, in the due process, it becomes stable, and they both obtain charges which are opposite, positive and negative, and then later on these charges attract. That means the positive and negative come together to form the ionic compound, which is sodium fluoride. So the same thing happens to sodium chloride. Just like sodium fluoride, we form sodium ion and the chloride ion, and then the two come together to form an ionic compound. In our second example, we are going to use magnesium chloride as our ionic compound to show how ionic compounds are formed. And in this case, we shall need one atom of magnesium coming into contact with 2 atoms of chlorine, which will be produced by the chlorine gas. So basically, we have magnesium reacting with chlorine gas to form magnesium chloride. However, one thing to note is that magnesium has electronic configuration of 2, 8, 2. So that means magnesium has 2 electrons in the outermost energy level, these ones here. And in this image, we have this first electron and this second electron. However, magnesium would love to lose these electrons, it being a metal. For it to become stable, it must have an electronic configuration of 2, 8. That means these 2 electrons have to be lost. And in this case, lucky is magnesium, because in its vicinity we have 2 chlorine atoms. And when you look at the electronic configuration of chlorine, we have 2, 8, 7. And there are 2 atoms. That means 2 atoms each needing 1, and then we have 1 atom which does not want 2 electrons. So what happens? Magnesium will lose 1 electron to 1 chlorine atom, so that it becomes stable, and the second electron to the second chlorine atom. So what happens is that magnesium will now become stable and obtain a 2, 8 electronic configuration, while these other chlorine ions or chloride ions will now be having 2, 8, 8, because they both obtained this 1 electron from magnesium. So in the due process, they will now become charged. We shall have a magnesium plus as you can see, a 2 plus, and then the chloride ions will also now become negatively charged. So what exactly we are having? We shall be having magnesium with a plus 2 charge, and then we shall have 2 chloride ions that have a minus. So we shall have 2 chloride ions with minus. So these 2 chloride ions will be attracted by the magnesium ion, and in the due process, the forces that will keep these ions together will be the Coulombic forces of attraction, the ones caused by the negative charges and the positive charges. So these forces here will be our ionic bond. So that's how magnesium can form magnesium chloride whenever it's in contact with chlorine gas. During ionic bonding, there is transfer of electrons from the metal to the non-metal, forming opposite ions, and these ions coming together due to the attractive forces caused by the opposite charges. That's all about ionic bonding. Now let's have a look at our top 3 questions. Question 1. Which of the following is correct? Check through the objectives A, B, C, and D, and let me know in the comment section. And question 2. The electrostatic force of attraction holds ions together. Is this statement true or false? Still, just note it down in the comment section and we see your say about it. We are going to look at least 4 general properties of ionic compounds, and the first one is they are usually crystalline solids. Take note of the word usually and crystalline solids. In most cases, these ionic compounds are solids, and in some cases liquids. However, they are crystals. That's why we are saying crystalline. Remember, a solid can be either crystal or amorphous solid. And in this case, a crystal, we are meaning a solid that has a regular arrangement of atoms. So ionic compounds are usually crystals, just like you see salt crystals. One thing you will notice that if you go to your kitchen and try to find sodium chloride, which is our table salt or common salt, you will find it in form of crystals. And this is true for all other ionic compounds like calcium chloride and potassium fluoride. As you can see, we said ionic compounds, it should be a metal and a non-metal. Most of them will appear in the same way, and it may be hard for an individual to tell which one is which because they all appear crystalline. So ionic compounds are usually crystalline solids at room temperature and pressure. Property number 2, ionic compounds have high melting and high boiling points. Have you ever tried heating salt at home? You will realize that actually salt takes quite some time for it to start melting. This is because in a salt crystal lattice, you have to apply a lot of energy for you to separate these ions from one another. The positive and negatively charged ions are being held by very strong forces of attraction, and in this case you will have to apply quite enough heat for you to pull these ions apart. As such, it will always require a lot of thermal energy to overcome, and hence we shall always have high melting and boiling points compared to covalent compounds like water. Number 3, ionic compounds are usually soluble in water. We know water is a universal solvent, but they are insoluble in organic solvents like petrol and kerosene. I'm quite sure all of you have ever added salt to water, and you realize that after some time your water will be as clear as before, and that's because the salt will have dissolved in the water. So when you look at common salt, sodium chloride can dissolve in water, so will other ionic compounds. They will be able to dissolve in water. However, in petrol and kerosene, please give it a try. They will not dissolve. Your salt will not dissolve in oil. So one thing to note is that water is partially ionized, that means it is polar. So when you look at a water molecule, it will have some partial charges on it, partial negative and partial positive. And when you look at our sodium chloride, we shall have sodium ions and chloride ions. So these charges will always be able to interact. And there is a saying that always like dissolves like. So in this case, like water, which is polar, is also dissolving like sodium chloride or the ionic compound, which is also charged. So like dissolves like. In this case, our ionic compounds will be able to dissolve in our water. So when you look at salt in our glass, it will be very clear. It will be hard for us to see it because it will be able to dissolve. However, when you try to add it into our oil, it will remain insoluble. It will not dissolve in our cooking oil. So for that case, we can say they are usually soluble in water but insoluble in petrol. Lastly, our fourth property, ionic compounds conduct electricity when dissolved in water or when melted. In this case, whenever you dissolve an ionic solid, say sodium chloride, we shall stick to that, you'll realize that in water, the crystal will be broken down into its corresponding ions. So we shall be having sodium ions and chloride ions in water. And it's these ions that will always help in conducting electricity. That's why when you have your pure water, you realize that pure water will not be a very good conductor of electricity. However, when you add salt to it, it will easily conduct electricity. So this is basically because the ions are free to move in solution, that is to say when dissolved in water, or in molten form, that's when you have melted our compound. So if you try this setup here and you try to complete the circuit using our salted water, you will realize that it will actually conduct electricity. With the help of the bulb lighting, it will show that actually there is flow of electricity. So those are our top 4 properties of ionic compounds. As usual, I will end it with our top 3 questions. Number 1, why do ionic compounds conduct electricity when dissolved in water? Number 2, ionic compounds are insoluble in A. Kerosene, B. Petrol, C. Both A and B, and D. Neither A nor B. Then lastly, ionic compounds have low melting and boiling points. Is this statement true or false? Please let me know in the comment section below. So when you look at a chemical bond, it's basically a force that keeps atoms together. But for covalent bonding, we shall always be dealing with sharing of electrons. And in this case, we shall always be considering the outermost electrons, the electrons that are in the outermost energy level. So whenever a chemical bond is formed by sharing of electrons between two atoms, we shall always call it covalent bonding. And just like in ionic bonding, the compounds containing covalent bonds, we shall always call them covalent compounds. Just add covalent to compounds, then you have covalent compounds. So a covalent bond is formed when both reacting atoms need, take note of this, electrons to achieve an inert gas electronic configuration. So remember, for an atom to have an inert gas electronic configuration, it must have a fully filled outermost energy level. And in this case, we shall realize that some atoms will always prefer to gain so that they obtain all the maximum number of electrons instead of losing them. So in covalent bond, we shall only be dealing with atoms that need electrons to become stable. And in this case, these atoms will be the non-metallic atoms, non-metals. So ionic bonding, we saw transfer of electrons, but for covalent bonding, we shall always need the sharing of electrons because both atoms will prefer having more electrons added to them. By now, probably you might have an idea that nonmetals usually have 5, 6, 7 electrons in their last or outermost energy level. And because of that, usually to attain stability, they will always need electrons. So in most cases, whenever they are forming ions, they will prefer to gain electrons. However, when you have two nonmetals coming together and they both prefer gaining electrons, the best they can do is by sharing, mutual sharing of electrons, because none of those atoms will prefer losing, yet both of them want to gain electrons. So the best they can do is to share electrons. So whenever a nonmetal combines with another nonmetal, both needing electrons, a covalent bond will always be formed. Let's take a look at the following nonmetals. We have oxygen. You realize that oxygen has 1, 2, 3, 4, 5, 6 electrons. It has 6 electrons in the outermost energy level, and it needs more too, so that it can have a maximum of 8 in the outermost energy level. When you look at nitrogen, 1, 2, 3, 4, 5. Nitrogen has 5 electrons, and with that it will need 3, so that it also gains and obtain a maximum of 8 electrons. So as you can see, all these nonmetals actually prefer gaining, because losing will be much more difficult. And lastly, when you look at chlorine, it has 1, 2, 3, 4, 5, 6, and 7. So chlorine has electronic configuration 287, and it will need one more electron to become stable. And in this case, if chlorine comes into contact with other nonmetals, the best they can do is to share, because none of these atoms will be willing to lose electrons. So the best they can do is to share. So before we look at the process or the formation of covalent bond, we need to first have some examples of the covalent compounds that we might encounter in our day-to-day chemistry. When you look at the first example, we have methane, CH4, and the elements present, we have carbon and hydrogen. Remember, carbon and hydrogen, these are nonmetals, although hydrogen has its own issues. When you look at ethane, 2 carbon atoms and 6 hydrogen atoms, they are also nonmetals. So one thing you realize is that most of these organic compounds, from methane, ethane, ethene, and ethine, all these are covalent, and you'll realize they're actually gases. Remember, in our ionic compounds, we basically had solids. We go to ammonia. Ammonia, we have nitrogen and hydrogen. They are also nonmetals, so they will share. We have our alcohol, ethanol. This is also a covalent compound. This is a liquid. We have hydrogen sulfide, is a gas, carbon dioxide gas, carbon sulfide, and so on. So one thing to note, most of these covalent compounds are gases. So we shall see under the properties of covalent compounds what state are these covalent compounds in most cases. So these are some of the examples. You can maybe name some more compounds like water and so on, but these are some of the common covalent compounds. Lastly, we still have 4 more examples. We have carbon tetrachloride. This is a colorless and highly toxic liquid. Basically, we have our carbon and 4 chlorine atoms attached to it. We also have glucose, one of the main building blocks for starch and other carbohydrates. We have cane sugar, basically sugar found in sugar canes. And then lastly, we have urea, a chief nitrogenous end product of the metabolic breakdown of proteins in all mammals. It contains nitrogen and is also soluble in water. All these examples are covalent compounds. Finally, we come towards the end of our video, and we have our top 3 questions. Number 1, what do you mean by a covalent bond? We shall look at a detailed explanation of covalent bonding when we look at the formation of a covalent bond in our next video, but probably at this point you should be having an idea on what a covalent bond means. Number 2, When a dash combines with another dash, a covalent bond is formed. And lastly, number 3, choose the covalent compounds. We have methane, hydrogen sulfide, and carbon disulfide. Then lastly, all of these. Which of these objectives do you think is the covalent compound or a covalent compound? So covalent bonding is all about sharing of electrons between nonmetals. At least in our previous video, we had a look at the fact that whenever you have a nonmetal combining with another nonmetal, the type of bond will have to be covalent because both atoms will prefer gaining electrons. So in this case, let's have a look at carbon reacting with hydrogen, and we see how methane will form, because in this case our methane is our covalent compound. So if you look at this image here, we have our carbon having 4 electrons which are in blue. As you can see, we have 1, 2, 3, 4. These are the 4 outermost electrons of carbon. However, hydrogen electronic configuration is 1, and these ones in red are the 1 electrons for all the 4 hydrogen atoms. So when one carbon atom comes to bond with 4 hydrogen atoms, let us see what exactly happens. Remember, both of them prefer to gain electrons. So what will happen is that we shall form a structure of this type. We shall have carbon atom in the center with its 4 electrons, 1, 2, 3, 4, shown in blue dots. However, the 4 hydrogen atoms, 1, 2, 3, 4, they will all provide their 1 electron in red to be shared by the central carbon atom. So in the due process, we are going to see that we shall actually be having 8 bonds for carbon. Remember, at first carbon had 4, but now carbon is going to have 8. If you are to count the 8 electrons of carbon now, we shall have 1, 2, 3, 4, 5, 6, 7, 8. Because hydrogen is providing 1 electron each, and therefore, so we shall have a total of 8. So in this case, the electronic configuration of carbon will kind of be like this, will kind of be fully filled because it has 8. However, for hydrogen, which had 1, it will now be having 2 in the outermost energy level. 1 from it, this red one, and then the 1 from the carbon atom, giving hydrogen, each hydrogen atom, 2 electrons. And this is also true for the first energy level to be completely filled, just like for helium. So in this case, all atoms in the methane compound will be fully filled, and we shall basically be having the force of attraction between these electrons and the nucleus of the carbon atom, together with these electrons and the nucleus of the hydrogen atoms. That's what will keep these atoms together. So that's an example to show that actually carbon and hydrogen will be sharing electrons, but we are going to see a better version of it. In our previous video, we had a look at water being a covalent compound, and in this case we want to see how 2 hydrogen atoms can share electrons with 1 oxygen atom. When you look at this atom of oxygen, it has 6 electrons in the outermost energy level, all coming from its electronic configuration, which is 2, 6. However, this oxygen atom could love to have 8 electrons to be stable. The same applies to hydrogen. Each hydrogen atom here has 1 electron in the outermost energy level, and the electronic configuration of hydrogen is 1. But also hydrogen would love to have the maximum number of electrons, which is 2. So what we shall see is that this 1 electron will be shared by 1 hydrogen atom, and then this other electron will be shared with another hydrogen atom, as we are going to see. So what happens is that we shall form a molecule of this format. As you can see, one oxygen atom provides this one electron to be shared by hydrogen atom 1, and the same applies to this hydrogen atom. It will also bring its one electron. In this case, this hydrogen atom 1 will now be having actually 2 electrons in the outermost energy level. This one in X and the one in blue. Those are the 2 electrons. And the same applies to the second hydrogen atom. However, if you were to look at oxygen, oxygen initially had 6 electrons, but now it will be having 8 electrons. Let's count them. We have 1, 2, 3, 4, 5, 6, 7, the X, and 8. In this case, this oxygen atom will be having 8 electrons in the outermost energy level, and that is basically a similar electronic configuration to noble gases. In the due process, the hydrogen atom having 2, oxygen having 8, they'll both be happy and stable. That's how a water molecule is formed. So let us have a clear illustration of a water molecule. We know that oxygen has electronic configuration of 2, 8 in this water molecule. At least we shall assume it has 8 electrons in total. And then our water has 2 electrons. So here we have the hydrogen atoms in blue. They have their 1 proton and their 2 electrons being bonded. One provided by the hydrogen atom, another one provided by the oxygen atom. So hydrogen has 2 electrons, as we had seen in our previous slide. However, oxygen, the innermost energy level, will have its 2 electrons. They are here. They are within the first energy level. Then we have our nucleus here with the protons and neutrons present. And then lastly, we shall have the 8 electrons being shared. So this is 1, 2, 3, 4, 5, 6, 7, 8. So this shows that actual oxygen will be having the 8, will appear to be having 8, as hydrogen will also appear to be having 2. In this way, they will be happily bonded, and this will be what we shall call a covalent bond. So the force of attraction from the nucleus of the oxygen atom, these protons in the oxygen atom will always be pulling the electrons being shared. And the same applies to the nucleus of the hydrogen atoms. They are also pulling these electrons being shared. And this kind of force will keep these atoms intact. It will keep the hydrogen atoms and the oxygen atom intact, because they'll be pulling and sharing these electrons in the due process. That's how a covalent bond is formed. In this video, we have only looked at 2 examples, that is formation of methane and formation of water. However, we know that we have very many covalent compounds like carbon dioxide and ammonia. Remember, most gases are actually covalent compounds. So feel free and try and see how the covalent bond will take place in these compounds. So let's now have a look at our top 3 questions. Question 1. Which of the following is correct? A, B, C, or D? Question 2. Carbon tetrachloride and urea are not covalent compounds. True or false? For this question, it could be easier if you had a glimpse of our previous video. We had a look at the different examples of covalent compounds. Lastly, question 3. In the formation of covalent bonding, dash of electrons takes place in the dash shells of atoms. Feel free to let us know in the comment section what you think about these 3 questions. So before we look at the four main properties of covalent compounds, here are some of the practicals or hands-on practicals that you can try out in the comfort of your home to test for the properties of covalent compounds. Take a sample of cooking oil, try and dissolve it in water or ethanol. Does it dissolve? So try it out and see whether cooking oil will be able to dissolve in our water. Then too, have you ever observed a burning candle wax? If not, take a candle wax and observe it burning. How much time does it take to melt down? I'm sure on birthdays you have ever tried observing a burning candle wax. Then lastly, take a pan and add water to it and let it boil. Do you know the boiling point of water? Is this boiling point of water high? At least these three can help you kind of gauge some of the properties of covalent compounds and then try to align them with the four properties we are going to look at today. Property 1, they are usually liquids or gases. When you look at most of the compounds that are formed by covalent bonding, you realize that actually most of them are liquids or they are gases. Take an example of water, cooking oil, and then methane, ethane being gases. You will see that most of the compounds are actually either liquids or gases. When you look at oxygen, it will be a gas. When you look at our methane here, it's also a gas. Cooking oil is a liquid. Water, as we had seen it in our previous video, it's also a liquid. Alcohol is also a liquid. So we shall see why actually most covalent compounds are liquids. But take note, we have said usually. That means we can also have some solids. Some solids like glucose. Glucose is a covalent compound and it's a solid. We have urea and wax, like we had seen on our previous page, talking about the melting of a candle wax. However, it is strongly believed that covalent compounds are usually liquids or gases, as we shall see the reason behind that. So we have seen that most covalent compounds are actually liquids or gases, and the reason is going to be hidden behind this second point, that covalent compounds have usually low melting and boiling points. So in case you have low melting points, that means you are likely to be a liquid, and in case you have low boiling points, that means you are likely to be a gas. That's why our previous point we saw most covalent compounds being liquids or gases. Now let's use water and then see why these covalent compounds are actually gases. So here we have our water molecule, we have our hydrogen atom, two of them attached to oxygen. This is the same structure that we had seen in our previous video. So we have very many water molecules, but you realize that these water molecules are being bonded to neighboring water molecules. So this is water, let us H2O. So one H2O is attached to another H2O. You realize that hydrogen is attached to oxygen, hydrogen to oxygen, or oxygen to hydrogen. So we have weak intermolecular forces of attraction between different molecules. If we call this molecule 1 and this molecule 2, we shall realize that actually we have some weak forces of attraction. So this bond here between the oxygen and the hydrogen is the weak intermolecular force of attraction, which will always put these molecules together so that they are closely packed like in liquids. However, these forces are very weak, and on slight warming they can easily break down because they are weak. Intermolecular force means between molecules. So this one basically means between molecules. So because these compounds generally have weak intermolecular forces, they can easily break on warming, so that these compounds either melt if at all you had a solid, or boil if at all you had a liquid. So during boiling, when these forces break, these particles or molecules of water can then escape into the gaseous phase. So that's why these covalent compounds will always have low melting and low boiling points, because of the weak intermolecular forces of attraction. But please note, we still have a strong covalent bond between hydrogen and oxygen. So here we have a covalent bond, a strong one. It's not these covalent bonds that are formed between the water molecules that break. It's the weak intermolecular forces of attraction between the different molecules and not between the atoms within the compound. Hope we get that. So covalent compounds usually have the low melting and boiling points. For example, when you look at water, water has a boiling point of 100. I don't know whether that's high or low, but basically water having a boiling point of 100, that's quite low, because when you look at the boiling point of the melting point actually of sodium chloride, it is in 801, but in this case our water has 100 degrees Celsius. So if you look at other boiling points and melting points, if you look at hydrogen gas, look at the melting point of hydrogen, it's in negative 259, while its boiling point, it is in negative 253 degrees. These are quite low values. Oxygen melting point negative 218, while boiling point we have negative 183. So you realize that actually these gases will have to be gases at room temperature because their melting and boiling points are quite low. We have ammonia negative 78 and negative 33. Property number 3. Covalent compounds are usually insoluble in water. This means they do not dissolve in water, but they are soluble in organic solvents. So when you look at covalent compounds, they are actually non-polar. They don't have charged parts. In our previous video, we had a look at what polar means. For example, when you look at a water molecule, this is our oxygen attached to 2 hydrogen atoms. So this is our water. You'll realize that hydrogen atoms are partially positively charged. This is what we mean by being polar. Ionic compounds will always dissolve in water because they are also charged. However, our covalent compounds are not charged. That means they are non-polar. And there is a saying that like dissolves like. So using this similar theory, polar dissolves polar. Polar will also dissolve polar. And as such, our covalent compounds being non-polar, they can't dissolve in our polar water. However, they will be able to dissolve in our non-polar organic solvents. So covalent compounds like lipids, like the hydrocarbons, the alkanes and alkenes and so on, all these ones will not be able to dissolve in water because their chemical makeup being non-polar will not allow them to fit into the society of the polar water molecules. As such, only a few covalent compounds can actually do that. Compounds like urea, glucose, and then sugar. These are some of the few covalent compounds that can actually dissolve in water. So covalent compounds are usually insoluble in water, basically because they are non-polar. Property 4. Covalent compounds do not conduct electricity. We know that to conduct electricity in solid state, you need electrons. However, if you are in solution or molten form, that is to say in liquid form, you need at least ions so as to be able to conduct electricity. However, when you look at covalent compounds, most of them do not contain charged particles. When you look at your oil will not be able to conduct electricity. When you look at water has no free ions to conduct electricity unless when you dissolve some ionic compounds in water, that's when it will be able to conduct electricity. As such, covalent compounds cannot conduct electricity because they don't have free moving ions that can move from one place to another to conduct the electricity. In that case, it means that if you have your common salt, for example sodium chloride, your sodium chloride will be able to conduct electricity because the positively charged sodium ions and the chloride ions can easily move within the solution to conduct electricity. However, for glucose, when you look at glucose, it has no free moving ions or charged particles to conduct electricity. As such, your bulb will not light. So pure water, which is free from dissolved ions, it will be safe. It will not require you to worry about it, so it will not conduct electricity. Finally, we reach our top 3 questions. Question 1, most covalent compounds are dash in water but dash in organic solvents. Question 2, name 2 covalent compounds which are soluble in water. Remember, we said usually they are insoluble in water, but still that means there are also some cases where we have these compounds which can dissolve in water as well. That's why we used the word usually. Then lastly, question 3, why most covalent compounds do not conduct electricity. Still here we have said most. Please, you can try and find some covalent substances which can conduct electricity. So, giant covalent structures can also be known as giant atomic structures. This is because these structures normally contain very many atoms. Many atoms come together to form something big, something gigantic. However, you will realize that for most of the substances we are going to look at today, for example graphite, diamond, and then silicon dioxide, they are going to have very high melting and boiling points. When you look at the simple covalent structures, the ones we looked at previously, substances like oxygen, carbon dioxide, methane, and so on, these were actually falling under simple covalent structures. Although we didn't group them into that category, but that's where they fall. And we had seen that actually these compounds had low melting and boiling points. However, for the giant atomic structures, we are going to see that they usually have very high melting points, and we shall see the reason behind that. So our first giant atomic structure is going to be diamond, and we are going to see its structure in terms of bonding. When you look at this structure here, it is representing the structure of diamond, and we have some spheres here. These black spheres are actually representing carbon atoms. Diamond is basically carbon, so diamond is an element. However, we shall see that each carbon atom, let's put emphasis on this carbon atom here in the center. We shall see that this carbon atom is bonded to 4 other carbon atoms. Remember, carbon has 4 electrons in the outermost energy level, and if it bonds to 4 others, it means all its 4 electrons have been used, because the bonds between these carbon atoms are actually covalent bonds. So each carbon atom is bonded to 4 other carbon atoms in diamond. So each carbon atom is bonded to 4 other, let's write 4 other atoms of carbon. So diamond is basically made up of carbon atoms that are covalently bonded to one another. So because of this type of bonding, carbon has no free electrons, and because of that it will not be able to conduct electricity, because all its electrons are actually used in covalent bonding. However, because of this 3-dimensional structure, carbon can form a very large structure of diamond, and in this case this diamond will be quite hard because of the strong covalent bonds between all the carbon atoms. So because of these many covalent bonds, we shall see that this diamond is actually very hard. So as such, diamond is basically a hard substance, and it has a very high melting point. We had seen that most covalent substances actually have low melting points, but in this case we're having a covalent element. We have only carbon atoms in diamond, and it has a very high melting point of about 4000 degrees Celsius. So because of these facts, we shall see that diamond can be used in making cutting tools. So because it's hard, it can be used in making cutting tools. And maybe one other aspect of diamond, apart from making these glass cutters, is that it has a very high heat transmission capacity. It can easily transmit heat even better than silver. Even if it does not conduct electricity, here does not conduct electricity, in terms of heat, it is good at conducting heat. Does not conduct electricity. So there are many other uses of diamond apart from being used as a cutting tool. It can be used as a jewelry and many more. At least I made a video on properties, uses of diamond. You can please check it out in one of my playlists. So that's all about diamond. Basically, the main focus on diamond will be the 4 carbon to carbon bonds, covalent bonds. So for this diamond to melt, we shall have to break these covalent bonds, and these are quite strong. That's why we shall have these high melting points. Our second giant atomic structure is graphite. Graphite, just like diamond, is also basically carbon, made up of carbon atoms only. However, the arrangement of these carbon atoms is quite different from that of diamond. We had seen that in diamond we had 1 carbon atom bonded to 4 other carbon atoms. However, here in graphite, if we look at these spheres here, are going to represent our carbon atoms. However, if you look at the arrangement in graphite, we shall see that each carbon atom is actually bonded to 3 other carbon atoms. When you look at this other carbon atom here, it's bonded to 3 other carbon atoms. This one here, 1, this one 2, and this one 3. So unlike in diamond where we saw 1 atom bonded to 4 other, in this case each carbon atom is bonded to 3 other. And because carbon has this electronic configuration, if it creates 3 other covalent bonds, it will always have 1 free electron redundant. As such, these free electrons will always be moving around within this structure of graphite. So because of that, our graphite can conduct electricity. I made a detailed video about the structure, properties and uses of graphite. You can try and check it out because I will not be so detailed in this case. So because of this 1 to 3 form of bonding, 1 carbon atom bonded to 3 other carbon atoms, we shall see that we shall form a hexagonal layer or ring of atoms. So as you can see, a hexagonal means they are 6-sided. If we are to count 1, 2, 3, 4, 5, 6, and these hexagons will create what we shall call layers. So we have this as our upper layer, and then we have this other one as our layer 2. So you realize that in graphite we have different layers. However, these layers are being held or put together by weak forces of attraction, and these weak forces of attraction, we call them van der Waals forces of attraction. Van der Waals forces of attraction. They're actually weak. That's why when we apply some force, these layers can easily slide past one another. So graphite is relatively soft and can conduct electricity. However, it also still has a very high melting point of 3600 degrees Celsius roughly. So most of the covalent substances we had looked at actually had low melting points, like water melting at 0 degrees. However, for graphite, these are actually atoms, or this is an element, and it's gigantic. Because of the strong forces of attraction, the strong covalent bonds, it still has a generally high melting point. So because of its softness, it can easily slide. We can easily use it in making our pencil leads. So we just have to mix it with some clay, and then we can create our pencil leads. It's also good at working as an electrode because it can conduct electricity. So there are many other uses of graphite. You can please check them out in my other video, like I stated earlier. But basically, in graphite, the difference is that one carbon atom is bonded to 3 other carbon atoms, leaving behind a free electron, which will then conduct electricity. Lastly, we are going to look at silicon dioxide. There are many other giant atomic structures, but I felt we need at least to look at these 3. So silicon dioxide is well known for being the chief ingredient in making of glass. So this is basically sand, and the structure of silicon dioxide is quite similar to that of diamond. Remember, diamond is mainly made up of only carbon atoms. However, in silicon, we shall see that some of the carbon atoms, if this had been carbon, with the one in blue also carbon, but in this case, one carbon atom is replaced by silicon. So the ones in blue become silicon atoms, but the structure remains the same, just that in this image here, we have an open structure, but if you can go back, you can still follow through and see the difference. So we shall see that actually each silicon atom is bonded to 4 oxygen atoms. However, each oxygen atom, which is in black, is bonded to 2 silicon atoms. So if you can do the math, you realize that we shall come up with a ratio of 1 silicon atom being bonded to 2 oxygen atoms. So this is how we come up with the structure of silicon dioxide. It's well known for making glass, like I had stated, and also being used in optical fibers. So there are many other different examples of giant atomic structures, but we shall only look at these 3. Lastly, we are going to look at our top 3 questions. Question 1. Diamond and graphite are 2 common allotropes of carbon. I didn't talk about allotropes in this video, but at least I talked about diamond and graphite both being made up of only carbon atoms. So using your previous knowledge about carbon and its compounds, try to figure out whether this statement is true or false. Question 2. Graphite is used for making pencil lead electrodes, both A and B, or none of these? Let me know in the comment section below. Then question 3. Diamond and graphite have very dash melting point. So try to identify whether they will have high or low melting points. When you look at metal atoms, we shall believe that the force that keeps metal atoms together is going to be called metallic bond. Hopefully we believe it soon. And one thing to note is that we have somehow separated metallic bond from the other 2 types of bonding. is neither a covalent bond nor an ionic bond. Remember, an ionic bond, we had transfer of electrons from the metal to the non-metal. Transfer of electrons. However, under covalent bond, basically this was sharing of electrons between non-metals. So this is sharing of electrons. However, we are going to see how the metallic bond differs from these, although it might also look similar to one of them. However, we put it separate from these two types of bonding because the properties that arise cannot be explained by covalent bonding or ionic bonding. For example, metals are very good conductors of electricity in solid state. Moreover, remember, for ionic bonding or ionic compounds, they could only conduct electricity in solution or when molten. But for metals, they can conduct electricity in solid state. As we have seen, most metals are solids with the exception of mercury. So because of that, we can't somehow attach metallic bond to one of these two types of bonding, covalent and ionic bonding. Both ionic and covalent compounds cannot do so with the exception of graphite. In our previous video, we had a look at some of the properties of giant atomic structures where we had our graphite, and we basically said graphite can actually conduct electricity, although its bonds are mainly covalent in nature. It can conduct electricity. So with the exception of graphite, ionic and covalent compounds cannot be like the metallic substances that can conduct electricity in solid state. So let's look at the actual metallic bond. Formation of metallic bond. At least we have seen that most metals are actually solids. And if you were to look at the arrangement of atoms in these solids, we shall see that atoms are always closely packed. Although they are vibrating, they are closely packed. And basing on the atomic structure, we know that atoms are generally neutral. They have no charge at all, meaning that the number of protons and the electrons are usually equal. So if this is our structure of, say, sodium at atomic level, different sodium atoms, one after the other, one after the other. So what happens? We know that sodium actually has electronic configuration of 281. So each of these atoms has an extra electron in the outermost energy level. So how does metallic bonding arise or come about? When you look at each metal, its last electrons always have the potential of being delocalized. What do we mean by delocalized? Not being attached to a single atom, not being bonded to only one atom. That is to say, they are mobile, they are free to move around, they are free to roam, free to move. So let us see what we mean by this. If this sodium atom is free to move, what does that mean? When you look at each of these atoms, if this is atom 1, atom 2, atom 3, that means all these three atoms, each of them has one electron, and then within this very structure, electrons, this electron, and then this other electron, they can actually move around. So let us see what we mean by that. So in this image, we have, let us say this was previously our sodium atom. However, when it loses its one electron, this electron now becomes free to move. This one electron is this electron in the electronic configuration of sodium. So each of these atoms ends up losing at least its outermost electron. Losing, but it remains within the vicinity of this atom. So when the sodium atom obviously loses the electron, it has to become positively charged. That's why we see the positive charges here. So in metallic bond, what happens is that the outermost electrons of the atoms usually become free to move around. So they're not attached to a given atom. So we can't say that this electron here is fully and only attached to this metal ion here. So the positively charged ion is not also attached to only one electron, but this electron is free to move around just like the others. So all these negatively charged electrons you see here are free to move around within this structure of the metal or within these other atoms. So what do we mean by the metallic bond? Whenever the electron is lost, a positive charge is created. So this positive charge in relation to a negative charge, we know that if you have opposite charges, they will always attract. So opposite charges attract. So positive and negative. So this positive ion is attracted to this negative electron, just like this negative electron is attracted to this positive electron. So that force of attraction between the metal ion, which is positively charged, and the negatively charged free electron or delocalized. Delocalized is a better word than free because it shows that it's not in a particular place than actually being 100% free. So the force of attraction between the negatively charged metal ion, the positively charged, and the negatively charged electron is what will constitute a metallic bond. It is kind of electrostatic. So a metallic bond is electrostatic in nature. However, it is taking place between similar atoms. This was a previously sodium atom, now a sodium ion, sodium atom, now a sodium ion. So it occurs within the atoms of that metal. So basically that's how a metallic bond is formed, when the metal atoms lose the outermost electrons, and then the electrons will always be attracted by the formed metal ion. So if you look at maybe magnesium, if you look at its structure, that means for it will have two delocalized electrons moving around. So that's how a metallic bond is formed. We finally reach our top 3 questions. Question 1. Metallic bond is neither a covalent nor an electrovalent bond. True or false? 2. The force which binds various metal atoms together is called. I think that is self-explanatory. Then lastly, what do we mean by sea of electrons or electron cloud? I didn't talk about this, but I felt it's worth noting in our top 3 questions. Try and find out what we mean by sea of electrons. At least one thing I'm certain, in my previous page, I somehow had it in one of the images as sea of electrons. It was present right in front of our eyes. So what do we mean by sea of electrons or electron cloud in regard to metallic bonding? Property number 1, metals are good conductors of heat and electricity. In our previous video, we had seen that when you look at the metallic bond, because of this metallic bond, we always have some free stroke delocalized electrons that we are always able to move around because they are not attached to a given atom. So because of these delocalized electrons, obviously we can have our electricity, the flow of charge. So metals are actually good at conducting heat and electricity. That's why whenever you are trying to boil something, maybe in an aluminium saucepan, you always have to hold it with an insulator because they tend to easily become hot because they are actually good conductors of heat. So silver is the best heat conductor, while also maybe something to note, copper is a better conductor than aluminium in terms of heat. So metals are good conductors of heat and electricity. So whenever you have electricity around, don't try touching a metal because it could be conducting that same electricity. Property 2, metals are lustrous. This is a property that talks about how shiny a substance might be, especially because of its ability to reflect light. So metals tend to reflect light. If at all they tend to be dull because they are normally a bit gray, in this case, if they are freshly cut, if you cut it with a knife, some are not so hard, they can easily show you how shiny they are. They tend to be lustrous. For example, you can see silver, it is shiny, gold, it tends to shine, and so on. Even copper tends to shine. So metals are basically lustrous to a larger extent. Property 3, metals are usually hard and strong, and with this property it means they can easily withstand stress. They can't easily be affected by strong forces. That's why when you look at iron in form of steel, we can easily use it in construction of things like bridges and maybe long storage houses. So metals are basically hard, with the exception of some few soft metals that can easily be cut by even a knife, like potassium and sodium. These are actually soft, but most other metals, like in this image, it can be quite strong and hard, and for that case it can't easily bend, it can't easily extend, and so on. So this is a nice property for metals because in construction we can always look up to them to produce good structures. Property number 4, metals are ductile, meaning they can be drawn into wires, thin wires. So when you look at silver and gold, these are the most ductile metals. So all metals, whenever you try to apply some force on them, their atoms will tend to slide past one another, creating a thin layer of these atoms. As such, you can easily create these thin wires of metals. That's why, as you can see here, we have our copper wire because it could easily be stretched. That's why we can say that metals are actually ductile. This is just a terminology to mean they can be drawn or made into thin wires. Property 5, just like we have seen metals are ductile, they are also malleable. This is another property talking about how these metals can be hammered into sheets. Obviously, hammering, we are meaning heat. You get something strong and put some good force on them. So because the atoms can easily slide past one another, they can also roll past one another, creating a structure like this, aluminium foil. So aluminium foil is made because aluminium can easily be turned into a sheet. That's why we are even able to make saucepans made up of aluminium. So metals are malleable. It's also a good property that is essential in our day-to-day lives. Number 6, metals have high densities. We know that density is equal to mass over volume. So when you look at the mass per unit volume of most metals, they are actually high compared to other covalent substances like water. So when you look at iron, copper, these are relatively high densities. However, sodium and potassium, maybe with cesium, these ones tend to have low densities. But the general trend will be that most metals have relatively high densities compared to other substances. Point 7, metals have high melting points and boiling points. They are also quite high. When you look at metals, we had seen that metals have very many electrostatic forces of attraction. And because of these electrostatic forces of attraction between the metal cation and the cloud of electrons, you need to apply a lot of energy for them to melt. So we shall always have high melting points, and in the same way we shall have high boiling points. So with that case, we shall see that actually the boiling points of these metals are actually similar to ionic compounds and not similar to covalent compounds. However, we have some metals like mercury which have low melting points. That's why we shall always have our mercury being a liquid at room temperature, because it tends to have a low melting point. So when you look at these metals here, the melting points are quite high. However, we shall see that some group 1 metals like sodium and potassium, they actually have low melting points. So group 1 and the ones below, for them they tend to have low melting points. But this does not mean that the general rule of thumb for metals is that some might have low melting points. No, actually most metals have melting points, just like this point has been stated. Point 8. Metals are sonorous, meaning they tend to produce a ringing sound. So when you somehow hit them, they tend to produce some sound. That's why they are normally used in bells and violins. So when you somehow play with metals, get something and you hit them hard, you'll find that they'll produce some ringing sound. So metals are good at that. Unlike non-metals, they may not produce that kind of sound. So the term sonorous means they tend to produce a ringing sound when hit. With hit we are meaning HIT. We shall end with our top 3 questions. Name the metal which is the best conductor of electricity. Remember, we are looking at the giant atomic structures, and we said actually diamond is the best at conducting electricity. But what about in terms of metals? Which metal do you think is the best in terms of conducting electricity? Let me know in the comment section below. Aluminium is a better conductor of heat than copper. Do you think this statement is true or false? Why are cooking utensils made of metals? That could be self-explanatory, but still give it a try.